Okay, so hello everyone. I'm Aisha Rahman, and I'm the chair of the IEEE Women in Engineering Albuquerque Section Affinity Group. Welcoming you all to our monthly public talk series. We would like to thank Dr. Naeini, Assistant Professor in the Electrical Engineering Department at University of South Florida, for joining us as our key speaker. Before joining USF, she was an assistant professor in the computer science department at Texas Tech University. She received her PhD degree in the electrical and computer engineering with a minor in mathematics from the University of New Mexico in 2014. Her research interests include leveraging data analytics, network science, signal processing, graph signal processing, and graph-empowered machine learning to integrate security and reliability measures, as well as socio-behavioral models into the design and control of cyber-physical human systems. She will be discussing the topic graph signal processing for analyzing data from interconnected systems. So again, thank you so much for making time out of your very busy schedule to join us. And I'm going to pass it down to our key speaker for today, welcoming Dr. Naeini.
Thank you so much for the introduction, and thanks for having me here. It's a great pleasure to be back at UNM, at least virtually. I want to start this talk differently in the sense that I usually start technical from the beginning, but because this is the IEEE Women in Engineering, I'd like to start talking a little bit about my journey in academia first, and I'll get into the technical discussion of our talk today. So the first thing I want to say is that I'm a proud UNM graduate. I got, as was mentioned, I got my PhD in electrical engineering and computer engineering, and with a PhD in minor in mathematics from University of New Mexico in 2014. This is the picture of me with the logo on the graduation day, which was a moment to be proud of. And I still look back at UNM and the IEEE Women in Engineering and IEEE Albuquerque section are really dear to my heart, because many of the things that I've achieved over the years started with my work at UNM. So it was the beginning, or actually a critical point of my career, because I started obviously my education before UNM, but UNM was the place that I really decided that, okay, I want to stay in academia and I like to do research and I like to continue what I've been doing. So I'm just sharing some memories with you here. My journey at UNM, I started in 2009. This is the picture of me at Dog Pond in my first semester. Obviously, I miss the campus of UNM every day, and I hope you enjoy it as much as I did. To be honest, I've been to many campuses, but UNM has one of the most beautiful and coziest campus of all, because you don't see like cars passing by. It's not like those crowded street-like campuses, so I really like it. And Dog Pond was my favorite spot to go and relax, and when I had a difficult research day or something, I would go there and that would free my mind, and it was really my favorite spot on the UNM campus. So I hope you enjoy Dog Pond as much as I do. I don't know how it looks now, but this is how it looked back then. I also experienced a lot of interactions with the peers and researchers through attending conferences while I was a student at UNM. These are some pictures from me attending these different events, and those were the moments that I realized that this is the place that I want to be. I want to keep doing that, keep going to conferences, keep talking about my research. And that was basically, these experiences kind of added up together, leading me toward this path that I'm at currently. And while I was at UNM, I was the president of Society of Women Engineers in 2012, almost 10 years ago. And we attended the SWE, the Conference of Society of Women Engineers, that year with a group of wonderful female engineers from UNM. And that was the first time that I participated in a poster competition. And I won one of the best poster awards. And this is that ceremony that it was a very kind of unique experience for me. And at that point, I was like, I want to do this again. I want to participate in many more competitions. I want to be on the stage again. So that kind of set the stage for a lot of more milestones and that I set for myself. And this is me getting the Outstanding Graduate Student Award from Albuquerque IEEE section, I think in 2013. And then I got the Outstanding Graduate Student Award from College of Engineering. So overall, my path through UNM was really fruitful, and I had a great experience attending all these events, and I was always looking out to find opportunities to engage in these kind of gatherings and conferences and events, because that's how basically you can grow. And after UNM, I joined Texas Tech University, as it was mentioned. And one of the main reasons that I like Texas Tech University and I started my career there was kind of, it felt close to my home at that point, because I don't know if you know or not, it is just 5 hours drive into Texas from Albuquerque. And I kind of felt that, okay, I'm still close to Albuquerque, which was my home at that point. And I started my career as an assistant professor in the computer science department. And I started my research group with two wonderful female PhD students. These ladies that you see in the picture on the left are now doctors doing great things and research at their current positions. They have been graduated. Basically, I continue trying to achieve the milestones that I had in mind. I got the Outstanding Faculty Award at Texas Tech, and I transitioned later to USF, and that's a PhD student, who was my first PhD student, graduated at USF during the pandemic. So that's why this is the picture I have from her graduation and her defense date. She was the first PhD student in our department who had to do the online defense because of the COVID, but nevertheless, it was a wonderful experience to see my first PhD student graduating, and she's now very successful doing research in a power and renewable company. And thereafter, and every time that one of my students graduated, that was a point of pride for me. I always enjoy looking at the success of my students, and I kind of wanted to wrap up this introduction with some of the things that I enjoy the most in academia. And I kind of obviously shared some of them through these pictures and memories with you. But one of the things that I also really enjoy is to work on the things that I care about and I see them impactful, and I can define the line of research to adjust with that. So this is a great flexibility to have. And the other important things that I experience in academia is that there is lots of learning and growing opportunities in many aspects, both in the theoretical aspects. You have to learn new tools, new technologies, research methods, teaching methods, and more. And it's always good to keep growing. And that's one of the great things in academia, that you don't have a dull moment, really. You always have to be dynamic and learn new things. Mentoring and working with the students and see them being successful is another great thing to enjoy in academia. And as I mentioned, networking with researchers and industry people through these meetings and conferences and panels is another thing that I always enjoy. Obviously, I kind of shared most of the things that are wonderful. There's obviously always other things involved, deadlines coming up. There's sometimes peak loads that you kind of feel pressured, but I think it all worth it at the end because of all these great things that you experience. So for those of you who are graduate students or you think about graduate studies and staying in academia, I highly encourage doing that and really going for that because it's a great experience. So kind of wrapping up here, and I'll be happy to talk about any of you who is interested to learn more about being in academia, but let's get into the technical discussion. So I want to tell you a little bit about what our research is about in our group. And the main focus of our research group is to leverage signal processing and machine learning, as well as network science to address lots of problems related to security and reliability of cyber physical systems, and particularly smart grids. And at the core of the research that we do is the graph or networks. For some reason, from very beginning, I was fascinated by graphs as a mathematical structure that allow you to abstract all these entities and connections in whatever system or context that you're thinking about. So I always was interested in graphs and networks, but not only that, because another reason is that we are surrounded by networks and graphs. Basically, many things that you can think about around you can be represented as networks and graphs. And the data that we have these days in abundance amount are also structured. So you can represent them with graphs and capture those interactions and structures in the form of graphs. So some of these graphs that we are interested in are in physical form, some of them in logical form when we talk about the data. But overall, all these structures, interrelations, and interactions among the entities and system in the system and data set can embed important information about the dynamic behavior of that system or the data. So it's important to capture those interactions and interrelations. So that's why in this seminar, I want to talk about networks, but not just the graphs or networks in a pure way, but in the form of data on networks, which we call them graph signals. And on the bottom of this slide, you see different examples of networks. For example, power grid network or structure, transportation network, the social network, which is a logical network. For example, this plot is actually this Facebook, my list of Facebook friends and their interactions and connections based on their friendship relation. And also the web network. These are, some of them are logical networks, some of them are physical networks, but overall, these networks are embedding a lot of important information that we can use in analyzing these interconnected systems. So again, just to make sure that the foundations of the graph signal processing that we want to talk about is clear, let's start with the most basic element of this discussion, which is graph. As we said, graph is a mathematical structure consisting of vertices and edges, and they can represent many relations and pairwise relations and interactions. So it's really an abstract entity. So here in this figure, you see that there are different forms of graphs. We have these nodes and connections. Sometimes these connections can be directional. Sometimes we can have weights associated with these links. But for this talk, let's consider the most simple form, which is a network of nodes connected through the links that are not directed, and we're not worried too much about the weights. So this is a graph that we are dealing with in this talk. And before getting into the actual discussion about graph signal processing, I want to say that there are lots of fields related to analyzing graphs in different forms. The first and most famous one is the graph theory, which is a relatively mature mathematical field. Graph theory is mostly focused on static graphs. There are lots of interesting algorithms that work on the graph. And but some of the issues that we have in that domain is that sometimes these algorithms and models does not scale well to the size of the real world networks. That's why there are like different domains like network science that are dealing with larger scale graphs and trying to understand the structure and dynamics of networks to understand the behavior and functionality of these systems and how it relates to the underlying structure. Probability theory and statistics has also been involved in the graph analysis, especially when we have larger scale graphs and it's difficult, for example, to visualize them. Statistical methods can provide us some understanding of how that network look like without actually being able to, without the need to really visualize it, or and many of those algorithms can be extended with these probabilistic methods. Machine learning and graphs have been also worked in hand for many years now. There are different ways that graphs get involved into machine learning. For example, we may want to learn the underlying graph structure by applying machine learning techniques to our data set. But sometimes we might have that graph structure and we might want to use it as, for example, an input to our machine learning model to help it improve its analysis. So there are different ways that machine learning and graph has been combined in different models and applications. And finally, graph signal processing, which is the focus of this talk, is about defining signals over the graph. And instead of obviously the Euclidean domain that we know signals in general form, and we want to use signal processing tool on those graph signals. And that's what I want to focus on for the rest of this talk. Okay, so the first thing that we need to know about graph signal processing is, what's the definition of a graph signal? For those of you who had the signal and systems class in the past, some of these concepts may be very intuitive and easy to relate to, but let's start very basic. So the classical signal processing defines a signal to be a time or space order sequence of measurements or values. So for example, in this blue curve, what you see is the temperature measurements over time. And this is an example of a signal that is over the regular time that is defined over the regular time domain. What is an example of this signal defined on a space? I think many of you know that it's, for example, image, right? Image is an example of a signal defined over space. So graph signal is defined in a way that we don't have that Euclidean time or space domain anymore. Instead, measurements or values are residing on the vertices of a graph. So for example, here you see a graph with 9 vertices or nodes that are connected in this form, and we have a vector of real numbers that are sitting on top of these nodes. So for example, these red bars representing the positive values, the blue bars representing negative values, and you see that we have different values for each of these nodes. This is an example of a graph signal. But since I'm going to show some examples of the applications in the context of smart grids, let me show you an example of energy graph signal. So the plot that you see here is a voltage angle graph signal, which is showing the measurement of the voltage angle at different buses of power system, which in this case is IEEE 118 test case. So in this plot, these nodes or vertices are the buses of a power system, for example, substations or generators. And the lines are the transmission lines. So as you see, we are using the structure of the power system to define a graph signal, and we are adding the measurements on top of these nodes to form a graph signal. And the good thing about it is that instead of just working with those measurements purely and directly, now we are adding the information about how these measurements can be related based on the structure of the system. So this is just one example of an energy graph signal. Obviously, if you have other measurements and attributes that are of your interest, you can create graph signals for those measurements and values. And these measurements, for example, in power system could be collected from phasor measurement units. So in this case, we're not, as I mentioned, not too concerned about edge weights, but you can also define edge weights based on geographical or electrical distance between the pairs of nodes, or any attribute that is interesting for your or important for your application. So getting back again to some of the core concepts in graph signal processing, to be able to generalize the classical signal processing tools, which are very powerful on irregular graph domains such as, on the irregular graph domains such as, I'm just keep saying it, on irregular graph domains, we need to build the notion of frequency or the spectral domain, because if you remember, one of the key concepts we have in signal processing is that we have a signal and we, using a Fourier transform, we take it into the frequency or spectral domain, and we can do a lot of important analysis in that domain. But how can we define such domain for graph signals which don't have that regular Euclidean domain? So the first step toward that is to look at the graph Laplacian matrix. And there are different variations of the definitions for graph Laplacian. They're more or less the same. But here is a simple and straightforward definition where we have a diagonal matrix D, which on the diagonal element, you have the degree of the nodes, which is like the number of connections they have. And you subtract the adjacency matrix of the graph, which is a binary matrix with zeros and ones, indicating if there is a link between two nodes or not. And when you subtract these two, it gives you the graph Laplacian matrix, which is a matrix with some nice properties. First of all, it's symmetric, and off-diagonal entries are non-positive, and the rows sum up to 0. And we'll see why it's a nice graph soon. But so far, what I want you to remember is that this is the Laplacian matrix that is unique to this particular graph. So this graph Laplacian can act as a shift operator for us. And the shift operator, if you remember in classical signal processing, is the basis of defining many of these key operations on the signal. So if we have a graph signal F, which is, in this case, we are denoting it by a vector of the values that are associated with the nodes of this graph. And if we multiply this Laplacian matrix L with this vector, what happens is that it calculates the difference between the values over the adjacent nodes. So as you see, it's kind of extending the DSP notion of the shift operator. The Laplacian quadratic form of this matrix that you see here is showing the rate of change over the vertices. It's a measurement of smoothness. And let me explain that with this figure. So on the in the bottom, you see two graphs, and the left one has all the positive values, which are the red values, sitting on V1 to V4, and all the negative ones are V6 to V9, and we are transitioning from positive to negative, going to 0 at V5. So there is a smooth transition as far as the values over the nodes. This is a smooth signal, or a smooth graph signal, I should say. On the right, what you see is that we have switched the values at node V3 and V7. So there is a sharper or major change between the nodes in the neighboring areas. So this is a less smooth signal with larger variations. So in contrast to the name of this measurement, which is a smoothness, the larger the value you get, it means your signal is less smooth. So you see for the graph that is on the right, we have a larger value for the Laplacian quadratic form, and the measurement of the smoothness is higher, which is indicating it's a less smooth signal. And before moving on, I want to quickly mention that the important point in this slide is that, as you see, the Laplacian or the graph Laplacian is telling us the rate of change. So, and the rate is related to the concept of frequency. So we are getting closer to building the notion of graph frequency domain. So let's look at the graph Laplacian decomposition. So if we decompose the Laplacian into its eigenvalues and eigenvectors, first of all, because the graph Laplacian is a real and symmetric matrix, you will have real eigenvalues, so we can sort them out. And the smallest of them will be a 0. And the reason that we consider there's only one 0 is because we are assuming that the graph that we are interested in is a connected graph. So there is one 0. If your graph has multiple disconnected pieces, you will have more zeros for each of those connected components. But in the applications of our interest, we assume that the graph of interest is connected. So we have 1, 0, which is the smallest eigenvalue. And if we look at the eigenvectors associated with these eigenvalues, we observe something interesting. So let's assume that our graph is this red graph that you see on the bottom. And these little bars that you see sitting on them representing the values of the eigenvector on those nodes. And remember, eigenvector of the graph Laplacian on its own is a graph signal. So the first eigenvector corresponding to lambda 0, which is 0, you see that we have the same bar at every node. So the value is constant over the nodes of the nodes of the graph. This is indicating that we have a DC component. So this is exactly like the DC component we have in classical signal processing. When we move toward the graph, the eigenvectors corresponding to larger eigenvalues, we observe that there is more variations in the values of the nodes. So for example, in the first one associated with lambda 1, we see that all the negative values represented by black bars are on the left side of the graph, and all the positive ones are on the right side of the graph, and there is a smooth transition in the middle of this graph. So this is a smooth eigenvector representing a low frequency component. As we move toward eigenvectors with higher associated with larger eigenvalues, we observe more variations and changes in the values of the nodes over the graph, representing a higher frequency in our graph. So as you see, there is a nice notion of frequency built over our graph using these eigenvalues of the graph Laplacian, and that's how it leads us to the definition of the graph Fourier transform. So on the right, you see the graph Fourier transform, and on the left is its mirror in the classical signal processing. So in classical Fourier transform, the eigenfunctions or the basis of the frequency domain are these complex exponential functions. So, and this is the Fourier transform, if you remember from your signals and systems class. And on the right, we have the graph Fourier transform. As we said, graph Laplacian is like our shift operator. The eigenvectors of graph Laplacian are going to be the basis of the graph Fourier domain. And when we look at the inner product of eigenvectors and our graph signal f, that will give us the magnitude of the spectrum, the spectral content at that particular frequencies, because frequencies are defined, as you see in the image below, based on the eigenvalues of the graph Laplacian. So this is an example of a spectral representation of a graph signal, and you see the amount of or the magnitude of each of these frequencies for a particular graph signal here. So this is a definition of the graph Fourier transform that we were looking for, and it helps us to take our graph signals into frequency domain to be able to do a lot of interesting analysis in a new domain. But before getting into some of those interesting functions that we can apply in the frequency domain, I want to introduce Again, formally another definition, which is graph signal smoothness. We already kind of mentioned it, but to kind of formalize this definition, to measure the global smoothness, we again can use the graph Laplacian in a quadratic form, and it quantifies the overall amount of fluctuations from one vertex to, from vertex to vertex. And we can have a similar definition for local fluctuation. So it's local smoothness and specifies the amount of fluctuation of the signal values from one vertex to another, again, using the elements of this vector, which is the multiplication of the graph Laplacian with our graph signal. So graph signal smoothness is an important feature that you'll see we are going to use in the applications that is coming up. Another interesting and important function that we do in signal processing is signal filtering. And the way that we do it is that we take our signal usually into the frequency domain and we apply a filter. So for example, low pass filter, high pass filter, to do different things depending on the application. So for example, you might be doing denoising of your signal. And when you multiply your function in the frequency domain by the filter, basically it filters out or removes some of the frequencies or changes and adjusts the frequencies, and then you can take your signal back to the time domain and do the analysis or the operation that you need to do on your signal. We can do the similar process for the graph spectral filtering. So using the graph Fourier transform that we just defined, we can take our graph signal into the frequency domain, and the filter this time is a matrix with the diagonal elements, which are functions of those eigenvalues of the graph Laplacian. So if you want to, for example, eliminate or amplify certain frequencies, you need to adjust the weights of these eigenvalues over the diagonal element, and you can have again different forms of graph filters for different applications. So for example, if you apply a low pass graph filter on a signal, it will retain the low frequency components, which are the ones that we discussed that show less variations and they're smoother signals. And naturally, they have more correlation among the data from the nodes. And for example, that can be used for identifying nodal communities which have similar values in their attributes. Another concept that is important in signal processing is sampling. And sampling, again, has lots of applications ranging from converting a signal from analog to digital, compression of the signal, and so on. And the process is that we reduce the number of samples in our signal, and we want to be able to reconstruct and recover our original signal with that limited number of samples that we took. The sampling in a graph signal can be defined in a similar way, that we want to use a subset of vertices and the values on a subset of vertices to reconstruct and interpolate the values at the rest of the vertices of the graph. However, the challenge here is that graph signals lack this regular sampling pattern, because you can't, for example, say, I want to sample every other node, because every other does not have a meaning in many graphs, because in many nodes, you have multiple branches going out. So there is no definition of every other or a regular sampling pattern in a graph. So there are different approaches that has been suggested, and this is still an active research domain. So new techniques are coming out. And the important thing is that how should we sample the nodes of the graph so that we get the most informative vertices, so that we can reconstruct our signal either perfectly or with minimum error. So another thing that's related to this discussion and is important is defining the bandwidth of signal, because many of these sampling techniques require band-limited signals. and many of the theories that are in classical signal processing have this assumption that for band-limited signals, so for example, you can use Nyquist rate to know how many samples you need. So first of all, the definition of bandwidth for graph signals can be similar to what we have in a regular signal. And we can define, for example, lambda b or b as the bandwidth if the magnitude of the spectral content after that point is 0. Or we might have approximately band-limited signals where the values after some point are insignificant. And if we have signals that are approximately band-limited, one way to deal with them is to apply an anti-aliasing filter to make them band limited, so that we can apply many of these theories to for sampling to these signals. But remember that this the reason that we say we use anti-aliasing is, if you remember from classical signal processing, when you sample your signal with this train of impulse, what happens in the frequency domain is that you get all these replicate copies of the spectral content, and if they get overlapped, the aliasing happen, which is not a desirable effect. So we want to avoid that happening, and that's why we want this band-limited property. And energy signals that I showed an example of that to you are generally approximately band-limited in most scenarios. So that's why some of these techniques that require band-limited assumption, we can apply anti-aliasing and then use this sampling techniques. And I'm going to show that to you in an example shortly. But before focusing on the application domain, which is smart grids for this talk, first of all, I want to say the techniques from graph signal processing is very general, and they can be applied to many other interconnected systems. So as long as you have this foundation that you can map your data or your system to these graph signals, all this discussion that we have here can be generalized to that application. But I'm picking smart grids as an interconnected system here to show you some of the applications. But why data from smart grids are very interesting, and why energy data analytics is important. So first of all, power systems are very important critical infrastructures, and our life depends on them because they provide electricity for us. So their reliability and security is also very important. So these systems are being equipped with more and more sensing and monitoring technologies, and there is a large volume of energy data these days that are collected from these systems. And if we can process them, we can improve many of the functions for these critical infrastructures. For analyzing such data, like many other data science applications, we use machine learning methods, statistical inference, time series analysis, and also, as we said, graphs also play an important role. But in our team, we want to introduce graph signal processing also as a tool to improve the energy data analytics. Obviously, like many other data science applications, we also need the domain-specific knowledge, including power engineering, economics, public policy. But an interesting thing here is that this figure on the right in the bottom is showing the result of a fairly recent survey from utilities that were indicating how important data analytics is for different functions in the power sector. So, and the range of functions that they have been using data analytics in is very wide, from the grid operation all the way to customer management and so on. So there is a large demand in energy data scientists these days in power industry. For the examples that I'm going to talk about, I'm going to focus on the transmission layer of power system, which is like their backbone, these high voltage transmission lines which transfer the bulk energy from generators to substations. But these techniques, as we mentioned, can be applied to different problems. And we also consider we have a cyber layer, all these monitoring devices, PMUs, that are collecting measurements from these systems. So let's start talking about the first problem that shows the application of graph signal processing into a problem in smart grid. And this is the state information recovery. So let me explain the idea using this figure. So let's say we have a graph signal on the left, and there is a region in this graph that is marked with the dashed red line. And we assume that the data from this region is not available or becomes unavailable because of many reasons. For example, cyber attack, or the failure in the communication system, or maybe there was no PMUs or measurement sensors there at all. For any reason it becomes unavailable, the problem can be formulated as a graph sampling and reconstruction process. Because if you remember, we said graph sampling is like having a subset of nodes, data from a subset of nodes available, and we want to reconstruct or recover the signal. And on the third or the rightmost figure, it shows the recovered signal, which you see in the process that we applied, and I'm going to discuss it next. It's kind of perfectly recovered the signal. But another important thing I want to mention about this figure is that, as you see, this is not like sampling in a classical signal processing that you have a regular pattern of sampling. It happened to have this clustered form in this example, where all the samples are on the left and the part that's not sampled is all in that region. So it's very different in nature in that regard. So the reconstruction process, as I mentioned, there are many different techniques and depends on the graph signal. But one example that is discussed here, it's through matrix multiplication, sampling, and reconstruction process, where it, again, is related to the graph Laplacian of the matrix. Here we are defining a sampling operator phi, which is a sparse matrix, basically telling where we should take the samples. And we have also a reconstruction operator where it consists of these eigenvectors of our graph Laplacian. And I'm not going to talk about the details of this and why this is working, but the thing is that it's like the dimensionality reduction problem in some sense, and we are reconstructing using this reduced dimension, using the eigen value vectors of this graph Laplacian. And one thing that, as far as the performance I want to mention here, is that for the graph signals of the power system or energy graph signals, we can achieve good reconstruction performance. But because these graph signals are approximately band limited, and the assumption of being band limited is important in this process, the majority of the error that we observe is because of the anti-aliasing filter, because we have to first apply that filter and then apply these techniques. Otherwise, it will not work. So the majority of error comes from the anti-aliasing filter. Another important thing is that where should we take samples? So I showed one specific scenario in that figure, but if we have the flexibility to choose where to sample, where should we take the samples so that we get the best performance? We have tested different scenarios, for example, taking the samples randomly in different nodes or based on their degree. For example, the ones that has highest degree, maybe we should sample them so that they provide more information. We can consider different centrality metrics, for example, page rank. Degree is another one that we talked about, or any other measure of importance for your nodes. We have also looked at the power attributes of some of these nodes. And for example, we can sample the ones that have larger loads. But out of all these techniques that we tried, one of them provided us better performance, and that's the one that considers the anti-aliasing error at each of the nodes. And basically, after you apply anti-aliasing and you reconstruct your signal, bring it back to the vertex domain, you will see that some of the nodes will receive more errors in the recovered value. And those are the ones that have higher variations. So if we put or take samples at those locations, overall, it can help with the process of reconstruction. Obviously, for some scenarios, we have the flexibility to choose where to sample, and for some scenarios we don't, like in the attack or cyber attack scenario, we don't have the flexibility of where to pick them. But this was just an experiment to see how these properties affect the sampling performance. Another thing is that obviously if the samples are clustered together, it's more difficult to recover the signal compared to the case that they're more scattered over the graphs. It's closer to like the regular pattern that we have for the sampling of classical signals. So these are the things that I wanted to share about this. But for the case that we have the flexibility of where to sample, it is close to the problem of PMU placement. So PMUs are those sensors that collect these measurements. So if we want to decide where to put them, and it's a problem in power system domain, we can again formulate it as a graph sampling problem. So the idea is that where should we put these PMUs? And we want to also minimize the number of PMUs while we have the better observability for the system and reducing the reconstruction error at the rest of the places that we don't have the PMUs for. So that's why you see there is an optimization formulation here that is trying to minimize the number of PMUs and also minimizing the error in the reconstruction. And we have solved this using a surrogate optimization technique, and also solving this heuristic, modeling this heuristic approach that, for example, we can use this anti-aliasing filter error as a guide for where to start putting these PMUs. So we can also add more constraints to this problem, but generally this is the way that we can think about this problem through the lens of graph signal processing. But one of the limitations of the previous technique was that we said it's based on the assumption that the graph is band limited. But many scenarios in power systems comes up that the energy signal is not very close to being band limited. So the anti-aliasing error could lead to large errors. In those scenarios, we can use other techniques for graph sampling and reconstruction. And one of them is based on graph signal smoothness. That's, if you remember, we introduced earlier in this talk. So the idea is that power system graph signals are generally smooth in normal conditions. That means that the value of the global smoothness overall should be small for a energy graph signal. So the other thing is that the local smoothness values of power system graph signals varies notably over the vertices. So if we take these two ideas, again, we can come up with an optimization framework with the goal of minimizing the global smoothness while maximizing the likelihood of local smoothness. So we need to come up with this distribution of probability distribution of local smoothness values for each of the nodes and their joint distribution, which is not an easy task to do based on the limited data that we have. So numerically and computationally, this would be difficult. That's why when we formulate this optimization based on maximizing the likelihood of local smoothness, in the next step, we further simplify this and say, instead of that and finding the joint distribution, maybe we can maximize the minimum likelihood value of local smoothness at each node. And again, if we want to further simplify and assume that these distributions are in the form of normal Gaussian distribution, which is not necessarily true, but is a reasonable assumption based on the performance evaluation that we did, then this becomes the simple optimization formulation that you see on the bottom, that is basically trying to find the local smoothness values with the minimum variation with respect to the mean and variance of local smoothness values. So this is, again, another process for reconstructing signals. So you want to reconstruct or interpolate the values in a way that it leads to this most smooth signal, that the values of the smoothness in the local nodes are following the distribution that we have for that system. All right, so the last problem that I want to quickly mention, and please let me know if I'm going over time, because as I said, I don't have a timer around me, but hopefully we are okay. This is the last problem I want to talk about, so that you can see that graph signal processing can be applied to different forms of problem and not just graph sampling that we discussed. So another problem is detecting and locating cyber and physical stresses in the power system. For this purpose, I mean, before I talk about this, let me tell you that we have done lots of studies, and there is some new studies shedding light on the fact that cyber and physical stresses have some signatures and patterns that are reflected in the graph signals, both in the vertex domain and also in the graph signal domain. So we want to use those signatures and patterns to develop algorithms and techniques that can help us to detect and locate these stresses in this system. So for that purpose, we are defining some example of cyber stresses, which here are defined based on the variations of the time series values. So this is a very simple model, but these models are defined in a way that we don't have abrupt change at the onset of the attack. So there's a smooth attack, which is more difficult to detect. And we also consider physical stresses. So for example, abrupt load change at the bus or failure of the line. So these are the type of stresses that we consider, and we want to add these stresses to the system and see if we can use the graph signal processing to detect these issues that are not easy to detect generally with some of these traditional techniques that are based on other methods. So the first technique for stress detection that I want to talk about is based on the graph Fourier transform. So if you remember, we defined graph Fourier transform that allow us to take our graph signal into the frequency domain. And what you see in this plot on the right, there is this green curve that's showing the spectral content under normal condition. So after we add like the false data injection attack, which is a cyber attack, or when we add a abrupt load change, we see that some of this frequency content is changing, particularly at the higher frequencies. Although this change is more obvious for cyber case compared to the physical case, but for the cyber stress detection, we can look at this change in the frequency content and use that as a mechanism to detect the failures, the stress. So here is the process basically. So we can look at the high graph frequency component content and calculate that using the filter. So we can apply a filter that only looks at the high frequency. So we remove the low frequency component, and then stress is detected by comparing the likelihood of that value compared to a threshold. So we have all this data that let us know which frequency content is normal and which is not, based on the distribution of these frequency contents. And we use that to define a threshold to allow us to say, okay, now the high frequency content is more than usual. So it's indicating something is wrong in the system. But this technique has some limitations also. First is that GFT, or graph Fourier transform, is an aggregated spectral representation, and it doesn't allow us to see where exactly things are happening. So it's not helping us with locating this stress. The other limitation is that, as you see in this figure, the physical stress do not show or create high fluctuations in the graph values in the frequency domain. So that's why we can look at other attributes of our graph signal. One of them is vertex frequency energy distribution, which is the analogous to the joint time frequency representation of the temporal signals, and allow us to kind of consider both the vertex and spectral domain content in the same measurement. And we again do the similar analysis. So we look at the VFED values at each time instant, and we detect a stress if the likelihood of that compared to the threshold that we have based on the data is above a certain threshold. And again, the probability distribution of these VFED values are estimated using the past measurements. So as you can see in this figure, again, we observe a peak exactly at the vertex that was under attack. So the VFED value at that point has increased, which not only allow us to detect the stress, it also allows us to locate the stress and where exactly it happened. So, and the last one that I want to talk about is the local smoothness, a technique based on local smoothness again, to detect and locate the stresses. So this time, what we do is that we are looking at the smoothness of the graph signal, because the stresses again show signatures on the time varying local smoothness. So on this figure on the bottom, you see that we have the local smoothness values over the vertices of the graph. And when we are looking at this under normal condition and when there is a stress on the system, okay, it seems that it's continuing to record.
Yep, don't worry about that.
Yeah, sorry, I think, am I going over time? What?
Yes, we are a little bit over time,
Okay.
but let's wrap it up.
Yes,
Okay.
I think I just, oh, actually, I was exactly at the end. So I just wanted to kind of say that graph signal processing is a very fascinating and fast-growing field, which extends the classical signal processing to the tools and techniques in the graph domain. And I just tried to show some examples of these techniques in the context of power systems. But these tools and techniques are very broad, and in general, they can be applied to many other interconnected systems. And I want to, at the end, kind of acknowledge all the help from my PhD students, particularly Mr. Hasnat, for the great work that he has done in this work. And I have projects that, with the goal of continuing this methods to new domains. And one of them is cascading failures in power system through this new NSF Carrier Award that I've got recently. With that, I would like to conclude and end this talk, and thank you all for listening, and I'm sorry that I went over time.
Thank you so much, Dr. Naeini. And especially thank you for all the fundamental concepts. I believe that was very needed, very well needed for us to follow through your talk. So let's see if anyone has any questions. Please feel free to unmute yourself, or we can also use the chat. And we just came back from spring break, and you know how UNM is.
Yeah, definitely.
It takes time for the students to wake up.
Yeah, that's normal. It's even true for me. So yeah, but I hope you all had a good spring break.
Let me begin with the questions. So I'm going to ask you a very general question. I believe that the participants are from UNM, so you're truly an inspiring profile. So I want to ask you if you have any advice for any student that wants to continue in the academia, then what path should they follow, or what should they prioritize?
Yeah, that's a great question. And I was kind of trying to motivate everyone with that few slides that I had at the beginning to say that this is achievable for everyone. And I was also a student at UNM, I just tried my best to not only find opportunities to improve myself and like participate in competitions, attending conferences. I was trying to create those opportunities. It was like you don't have to sit for those opportunities to come to you. You have to chase them, and you have to create opportunities to let yourself shine. So if you do a great work at what you're currently doing your research, I think it will automatically set you in the right direction. I highly encourage everyone to attend conferences. Maybe some of those conferences are not easy for everyone to attend, like national ones or international, but I remember I participated in lots of local conferences that were held regularly at UNM. I was attending the poster competition every year at UNM. Those were great experiences. So, as long as I think you have a good research profile, and you can always continue this path, and I'm sure you will enjoy like working in academia if you enjoy the research that you're currently doing.
Awesome. So any other questions from our audience?
You can always reach out to me later if you had any questions. I'll be glad to connect with you all.
Okay, I will be sharing your email as well. There's someone. Nope. Okay, I can see someone who unmuted his mic, Adedamola Desukan. I believe he has a question.
Oh yeah, hi Mia. Thanks so much for the presentation.
Sure.
I was just curious as to why you started off with graph signals. Was it what you wanted to do, or was it the research direction of your professor when you were in school? I mean, what exactly was the motivating factor?
Okay, and that's a good question. Actually, I was never heard about graph signal processing when I was a student. Actually, graph signal processing, as I mentioned, is a fairly new topic. It's a very fast-growing research domain. And what kind of brought that to my attention was that I was always interested in probability and signal processing. And always graphs fascinated me from the beginning. I started from computer networks, and then I kind of generalized it to social networks. And I thought, okay, everything has a graph behind it. So let's focus on the core of the graph. And at the end, it was kind of the marriage between my two interests. So I was interested in graph, and I was interested in signal processing. And we were seeing that there is a lot of data that has a structure and can be represented on top of graphs, and that's how it came to our attention. I would say a few years ago, actually maybe 3-4 years ago, that we started working on this, and we saw that it has tons of applications. And the good thing about it is that because it's a new domain, there is still lots of new theories that's being developed in this domain. So if you're someone who is interested in contributing in the theories of a field, that's a great place to be, both contributing in its application domain and also in the theoretical aspects of that. This is a very rich domain to work in. I hope I answered your question.
Oh, absolutely, yes.
Okay, great.
Thank you.
You're welcome.
So I think we will be wrapping it up for today. I'm putting up your email on the chat so that if anyone has any question, please email our speaker for today. And I I personally enjoyed today's talk very much. It was very detailed, and I haven't heard about graph signaling. I have heard about graph theory, and it's a very new domain. And I was starting to Google it, and I believe I will be reading more about it. So thank you so much.
You're welcome, and feel free to reach out to me if you had any questions. I'm always interested to interact and work with students, so I'm here for you all.
Thank you so much again. So
Okay,
have a
thank
very
you.
good evening, everybody. And I'm going to be ending the meeting now.
Okay, thank
Bye.
you. Bye-bye.
Bye. Thank you.
Thank you.